Pinterest is a visual discovery engine for finding ideas like recipes, home and style inspirations, and more. It powers over 500 million monthly active users globally. Our mission at Pinterest is to bring everyone the inspiration to create a life they love. My name is Zhan. I am a software engineer at Pinterest. Today, I'm happy to present how we build a distributed key value store for ML workloads at Pinterest, especially for ML feature serving. Machine learning and artificial intelligence powers Pinterest. They drive many key use cases like home feed, related pins, search, and ads ranking, which again deliver many critical business outcomes. For example, user engagement, revenues, and margins. But this is not the whole picture of ML ecosystem yet. We need a foundation to support the ML training and the inference infrastructure, such as networking, storage, and compute. For this presentation, we'll focus on the ML storage side. So one critical piece of ML infrastructure is ML feature serving. So what are ML features? Features are data points or attributes that ML models use to make predictions and decisions. So things like user behavior, item characteristics, or anything that's relevant. ML features can be produced in batch workflows or streaming jobs, and then they will be fed into ML model for inference tasks. So think of Pinterest as an application. So when you open the Pinterest app, it will show you a bunch of pins or ideas. What happens under the hood is for each user, we'll have a candidate pins, a bunch of candidate pins, and we need to fetch the relevant features for each pin and then feed these features into ML models to infer a score, representing how relevant each pin is to the user. Then we display the topmost, like let's say top K most relevant pins to the user that will show up on your home feed. With that, let's take a closer look at what the ML feature store needs to provide. For a functional perspective, it needs to support various methods for ML feature publishing, such as offline bulk updates and near real-time streaming updates. Again, these features need to be consumed by online applications. To fulfill those goals, the system needs to be highly available and sustain high throughput while maintaining low serving latency. Oftentimes, consistency is not a strong requirement over here. With those requirements, Pinterest's answer is to build a versatile key value store, what do we call it, KVStore. KVStore is a distributed schemaless key value store written in C++. It supports flexible ML feature publishing, accommodating bulk data uploads and streaming updates. KVStore is built with scalability and high performance in mind, ensuring reliability of this critical infrastructure component. In short, KVStore is the backbone of our ML and AI feature serving infrastructure. All right. Now that we have a good understanding of what KVStore is, why we built it, I'm going to walk through the agenda for the rest of the presentation. We'll do the overview of KVStore, including its architecture and some of the core functionalities. And then we'll talk about some of the challenges we faced while building KVStore, and then the optimizations we did to optimize and to overcome those limitations. Finally, we'll talk about the current state of KVStore in terms of its use cases and its scale at which it operates, and also explore some of the future directions we're exploring. All right, let's dive into an overview. We know that different applications need to consume features from KVStore, right? But then how are the data produced to KVStore? There are multiple methods. First, a common way is to have source data in different formats like sequence files, H files, or Hive tables. Those source data will be converted through a batch processing job, and this transformed data will be stored in Amazon S3. KVStore will then ingest those data in bulk from S3 into its local storage for serving. Typically, the speed of the bulk ingestion is limited by the EC2 network bandwidth. We can also support a variant of this mode by consuming incremental updates from Kafka after the initial upload has completed. This will ensure freshness of the data in addition to the bulk uploads. Alternatively, data can also be written into KVStore directly via streaming jobs, such as those coming from Apache Flink. So with this approach, we'll provide a pathway for incremental data processing in near real time. This is crucial for certain types of ML features. Now, let's zoom in and look at KVStore internals, especially how we support bulk updates, and streaming updates in what we call the read-only mode. When the requests come in to KVStore, you'll hit the API layer, which then route the request to the underlying storage engine. We use RosDB as a library to build a storage engine here. In KVStore, data is partitioned into different datasets, and a dataset is a collection of data pretty much similar to the concept table in SQL terminology. So a dataset will be partitioned into many shards. The shards will be distributed across a number of hosts, and we use Apache Helix for shard management. All right. So when the data is available in S3, meaning that a new set of data has been converted, it will prompt KVStore to load this data from S3 into its local storage. And once that bulk ingestion is completed, KVStore will swap the old version with the new version and use the new version to continue to serve the reads. Optionally, you can also ingest incremental updates from Kafka before we mark the new version to be ready for serving. This will increase the freshness of the data, as we just talked about. Alternatively, KVStore can also be operating in a mutable mode. What that means is the data is not available in S3 anymore. Instead, writes are directly issued to the KVStore. So the request flow is pretty much similar to the read-only mode, except that the writes now needs to be replicated within a shard. So what's happening is the writes will be issued to the leader replica, and then will be asynchronously replicated to the follower replicas. So this ensures data durability and availability while there are ongoing real-time writes. Okay, now that we talk about the KVStore internal architecture, let's look at how the data model and API works for the user. As we mentioned, KVStore is schemaless, allowing for flexible data modeling. A dataset is pretty much a collection of records organized in rows, and each row you may have multiple columns, and then within each column we may store timestamp version values. So this example table here is basically for illustration purposes. We can see how we can model a user profile, for example. In reality, for ML feature use cases, you may have one dataset for user features and another dataset for like pin or object features, where the row key can be user ID or it can be pin ID. And then the columns can be different kinds of ML features. On the API level, we'll support batch APIs. So you can do like get, put, delete on multiple rows at the same time. This will give us efficient operation to do batch updates or batch retrieval. All right. Well, all this look on paper, just like building any distributed systems, we face many challenges. And then we have to implement multiple significant optimizations to overcome these challenges to make sure our system can run reliably and efficiently at scale. Let's dive in. One of the major hurdles we're running into is network throttling, because in our environment, we have both bulk data movements from offline updates and real-time traffic from online serving that's competing for the shared network bandwidth. And network throttling can happen here because we use AWS EC2 and S3, and as long as the traffic exceeds the EC2 network allowance, packets may be queued or dropped in the network layer. What makes things worse is what we observed as microbursts, where there might be a tiny burst of network usage in the order of like milliseconds or microseconds level, so that you can even not observe with traditional network analysis tools or AWS CloudWatch metrics. But those are causing production problems, and then we suffer from those problems. To address those challenges, we started with building visibility around this network throttling by exposing metrics on top of based on the EC2 ENA network driver metrics. And then we apply multiple methods to smoothen the network bursts, including fine-grained S3 rate limiter to smooth out the traffic coming in and out of S3 to EC2, apply various ways of doing traffic pacing to avoid the network from being overwhelmed. For example, like this graph demonstrates, after you enable the ENA metrics, for the first time, Pinterest were able to see how network throttling happens in real time in production. And after applying some optimizations, we're able to pretty much eliminate most of the network bursts, hence reduce the amount of network throttling, and then improve the system performance. If you're interested to learn more about this topic, we just published an Edge blog about this. Feel free to check it out. Another challenge we faced is the typical noisy neighbor problems in multi-tenant platforms. KVStore can host different applications in single process, things like feed recommendations, ads ranking, internal tools, and they are sharing the same KVStore resource like queues, threads, and connections, and the underlying sharing the same set of hardwares like CPUs, RAMs, SSDs, etc. The resource contention can lead to performance degradations because like one tenant's heavy usage of KVStore may impact the others. To address this, we implement multiple strategies. On the user-facing side, we use rate limiting and quota management for resource control. This prevents any single tenant from pretty much abusing the platform and overload the system. In the system level, we further built multiple frameworks to prevent the system from being overloaded. For example, we're exploring priority-based load shedding to handle traffic spike in a more graceful fashion. We're also looking into how we can better enforce isolation of tenants and prioritization of traffic when there's a resource constraint. We have been looking to build these frameworks in the RPC layer. This is critical to ensure that we can minimize the noise neighbor problems in these multi-tenant systems, with the overall goal of making sure that our critical applications are less likely to be impacted when the system is overloaded. Another challenge we face is cost efficiency, and the problem statement is pretty clear. We need to ensure sublinear infra spend despite superlinear growth in usage and content. To achieve this, we did a pretty much a systematic way of addressing the efficiency problems at different layers. So on the bottom layer, at a service level, we look at all dimensions from compute, storage, and networking. For compute, we profile and optimize the performance of our service to reduce CPU usage. We conduct instance type evaluations to make sure we are leveraging the most cost-effective EC2 instance types for our applications. On the storage side, we use RushDB, and we leverage SSD compression to reduce the storage footprint. And then we build a tunable replication factor in our KVStore so that we can balance the cost of storage and availability of the system. On the networking layer, we build AZ-aware routing to minimize the cross-AZ data transfer, and then we further apply network compression to reduce the infra spent due to data transfer. On the platform layer, we are continuously sanitizing the platform, things like monitoring the cluster usage and right-size the clusters to make sure they match the actual demand. And we implement the garbage collection to reclaim resources that's not needed anymore. On the user side, how do we make users accountable is a big topic over here. One thing we implement is multi-tenant cost attribution, so we can actually track and monitor where the costs are coming from, and then identify areas for optimization. We also enforce quota in many places to avoid unexpected usage growth, which may cause big infra bills. All right, now that we've covered the KVStore system architecture and our production experience, in the next few slides, I'm going to walk through where KVStore stands today, and also look into some of the future directions we're exploring. Currently, KVStore pretty much powers all Pinterest ML feature serving use cases. Things like on-feed recommendation, which is critical for Pinterest user experience. It's also used for ads ranking and serving, which directly impacts our revenue. Over the years, KVStore has also evolved a lot that it started to support source of truth data. In fact, recently we have been evaluating all the in-house solutions, the open source solutions, and then consolidate all of similar key value storage at Pinterest into a single one. If you're interested in learning about our journey of database migration on Pinterest and how we got into this state, feel free to check out the end blog we published around this topic. As you can see, after the consolidation, we have been seeing a growing number of use cases to the platform in the past several years. At peak times, KVStore can handle 170 million requests per second at Pinterest. KVStore runs across 28,000 virtual machines in Amazon EC2. It has over 10 petabytes of data stored in SSD. And every day, it processes about 5 petabytes of data through bulk ingestion. This constant influx of new data keeps our ML models fresh and relevant. Now let's recap what we have covered today. Pinterest integrates AI and ML as its foundational technology, and we built KVStore to enhance the feature serving and recommendations. This is a pretty critical piece of how we render relevant content to the user. And we discussed how we build a feature store, especially how it intersects workloads from offline, nearline, and online domain. This means KVStore has to handle a wide variety of data ingestion and serving patterns. And we also covered how KVStore evolves based on business needs, ensuring reliability and efficiency at scale. Lastly, let's look ahead at some of the trends we're observing in the feature serving space, especially how that may reshape our storage architecture. We're seeing a strong push for near real-time processing because feature freshness is becoming increasingly important. We want the data to be as up-to-date as possible so that our ML models can make accurate predictions. We also see more adoption of this Lambda architecture that combines real-time data processing or near real-time data processing with batch processing for additional flexibility. We also see a growing need for higher throughput and low latency in general, that we need to handle terabytes of data transfer per second while maintaining sub 10 milliseconds latency. This prompts us to think about how we can reduce overhead of data fetching. For example, can we do compute pushdown by moving some of the logic closer to the storage? Or we embedding data at the application side for local serving and efficiency. The size of feature sets just keeps growing and it's becoming super large. But that means we could have 1 petabyte of data per data set or even more. That's becoming a norm in Pinterest, and we started thinking about how we can address that scaling challenge. Because it requires the storage system to efficiently process mass amounts of data. For example, the prompts out to think about, can we build more incremental processing pipelines efficiently in addition to bulk data overwrites? In the meantime, SSDs can be expensive, especially for such large data sets. So we're looking into how we can balance the cost and performance. For example, re-architecture our system to support tiered storage. Cool. All right. That's everything I want to cover today. Thank you for listening.